In this video, we're going to talk about the concept of conservation of energy. Conservation of energy suggests that for any closed system, and that's just saying that the mass is not changing, the total energy in this system is constant. Which means if I take any situation, and typically we're going to look at one object that is moving around. If that object is a ball rolling down a ramp, that object always has the same amount of energy. Assuming we don't consider friction, we don't consider air resistance, that would be other mass entering the system outside of that ball. Right? So basically we can say that the energy of the object before or at any earlier time is equal to the energy of that object at some later time or final time. So that is our basis for how we're going to solve problems with energy. Now, we also know there are different types of energy. So we're going to talk specifically about three kinds of what we call mechanical energies. You have gravitational potential energy, which is called GPE. And GPE we can calculate if we know the mass, if we know gravity, 9.8, and we know the height that we are elevated in a field. If we elevate something, gravity has the potential to do work, and therefore you have potential energy. If an object is moving, we have kinetic energy, and that is defined by 1/2 of the object's mass times its velocity squared. If an object has velocity, it is going to have kinetic energy. And the third kind of energy we're going to deal with is what we're going to call elastic potential energy. And this occurs anytime you have an object typically compressing or stretching a spring or some kind of elastic material, maybe a bungee cord. And it is defined by 1/2 K, which is the stiffness constant of that spring, times X squared, whereas X is how much that spring is compressed or stretched. So for the problems we're going to solve in this unit, we're only going to deal with these three types of energies. There are certainly other kinds. You have heat, which is thermal energy. You have nuclear energy, electrical energy. We've actually dealt with electrical potential energy, which is stored up in batteries. But for this unit, we're going to stick to these three. And if we know and can identify which of these exists, then we can start to set up our problem. So really for every problem, we're going to ask ourselves one of each of these three questions. In order to have GPE, you must be elevated above some arbitrary height. So if you can look at the object and answer the question, is it elevated? Then you know whether it has GPE and how much it might have. Now, kinetic energy comes from motion. So if we can answer the question, is it moving? Then we know whether or not it has kinetic energy at any given point. And in order to have elastic potential, we must be compressing or stretching a spring. So is it compressing or stretching a spring or some kind of elastic material? It could be a trampoline, it could be a bungee cord, right? So really that's all we're going to deal with. And if energy before is energy later, then all I'm really dealing with is any possible amounts of energy I could have. I could have gravitational potential energy before. I could also have kinetic energy before, or I could have elastic potential energy before or at any given point in a problem. Now, in most problems, you won't have all three, but you could. But most are going to only have 1, 2 of those elements before something happens in the problem. And then later, when the object's at a new location, well, it might have a new gravitational potential energy. It might have a new velocity and therefore kinetic energy, and it might now be compressing or stretching a spring. Right? So every single problem we're going to do in this unit comes down to that equation. And since each of these concepts have an equation associated with it, well, then you can derive an equation for it, which says that the mass times gravity times the initial height plus 1/2 m times the initial velocity squared plus 1/2 k times the initial stretch of the spring squared is equal to mass times gravity times the final height plus 1/2 mv final squared plus 1/2 k x final squared. Now, that looks like a big equation. If you understand the basic principle, energy before is energy later, and you know there are 3 types, well, then you can come up with this equation very easily. And again, most problems don't have all 3. And what we're going to see is a really simple example where we can assess the energy at any given point. So let's take an object. Let's get a little ball here. This ball's got some amount of mass. And let's put this ball on a ramp that's going to come down to the end. And it's going to hit this wall. But we got this spring that it's going to hit right here. Right? So this object could hit a spring. Right? It's going to roll down this ramp. Now, if it hit that spring would compress. Right? So let's say we also have a scenario where that spring has compressed a little bit, and we'll call that displacement x. That's how much the spring has compressed. Right? So let's draw this ball here. Let's say the ball is at different locations. Let's put the ball here. Let's put the ball on the flat ramp. Let's put the ball right at this point where it hasn't compressed the spring. And then finally, let's put the ball right in here. And let's say the ball has stopped at this point. Right? So you have all these different scenarios. Let's call this position 1, 2, 3, 4, and let's call that the 5th scenario. Right? So what we're really trying to find out is, since energy is conserved, then I know that the energy at position 1 is equal to the energy at position 2, which is equal to energy at position 3, energy at 4, energy at 5. Right? So if I know something about position 2, and I know all the energy there, well, then I can use that to find something about position 5, let's say the compression of the spring. Right? So these are all ways that we can kind of jump around in a problem. But what I do know is the total number of joules. If it has 10 joules of energy at position 1, then it has 10 joules at position 5. And so what we really have to do to solve a problem then is ask ourselves, well, what kind of energy do we have? Let's say at the top here that it has 0 velocity. And let's say it comes to rest at position 5. The velocity at 5 is also 0. So you have a scenario where the ball is at rest and elevated. And this is where we can draw some kind of line. Let's define the height of the ball as measured from that lowest point. And so we're going to say that right down here is our reference of GPE equal to 0 joules at that height. So in any problem, we get to define where we want to call GPE being 0. And a good practice is to pick the lowest point of the object and say that that is where there is no GPE. And therefore, anything above that is going to have energy. And then by doing that, you also don't run into a situation where you have negative GPE, which is possible if we set our reference at a different spot. So let's look at this object, and let's figure out what kind of energy we have at each location. At location 1, right, we're going to, at each spot, ask ourselves the 3 questions. Is it elevated? Is it moving? Is it compressing, stretching a spring? Well, at position 1, it's elevated, so we certainly have GPE. Is it moving? Well, we have no velocity, and it's certainly not compressing the spring. So at position 1, we have all GPE. And if we knew the height and we knew the mass, we could calculate the number of joules that are at position 1. At position 2, we have the same amount of total energy, but now we see that it is elevated, right? Let's call this the height at 2. But it also now has some amount of velocity that it has gained from falling down. And so at this point, we would say that there is GPE and there is kinetic energy, right? It's still not compressing a spring. So those are the only 2 types of energy. And let's look at position 3. At position 3, is it elevated? No. Is it moving? Well, certainly it's got velocity that it gained from rolling down the hill, right? So it has kinetic energy. And it's not yet hit the spring, right? So all of the energy is in the form of kinetic energy. It's all kinetic energy at this point at position 3, right? So in a problem like this, you might have them say, well, how fast is the ball going when it gets to the bottom of the ramp? And they might tell you the mass of the object and how high it is. It allows you to calculate the energy at position 1, the GPE. And then you would just set that equal to the kinetic energy at position 3. What about position 4? Well, we're certainly not elevated. We're certainly moving, and it's now touching a spring. But is it compressing a spring? Well, we actually, in this case, I'm going to say no. It's not yet compressing it. It's just hit the spring. So right now we're still all kinetic energy at position 4. Because that spring hasn't been compressed yet. And let's go to position 5. At this point, the ball has now come to rest. It is not elevated, no longer moving, and it is compressing a spring. So we're going to say it's all elastic potential energy at that point. Right? And if we threw a 6th spot right in here, if we threw the ball right at this point, right, then we would have 2 kinds of energy there. It would be compressing a spring, and it would still be moving a little bit. You would have some kinetic energy and some elastic potential energy at that 6th position, which I just added in there. Right? So again, all of these locations have the same total number of joules, but they are now, when work is done, in this case by gravity, and then work done by the spring, the energy changes to different forms. We don't lose energy, we just change to different kinds. Right, so if I look at this equation up above, let's look at what would happen from position 1 to position 5. Well, if I look at my equation up above, at position 1, I am elevated, I am not moving, I am not compressing a spring at position 1. At position 5, I am no longer elevated, I am no longer moving, but I am compressing a spring. And so this giant equation simplifies down into one equation that says that the mass times the gravity times the height at position 1 is equal to 1/2 K times that compression to position 5 squared. And if I knew all those elements, let's say I knew the compression, let's say I knew the height, I knew the mass, we know we're on Earth, well, I can solve for the one missing piece and find the stiffness of that spring. So we're going to use this process to start solving problems, make predictions about how fast an object is moving, how far a spring will compress, how high an object will bounce. All of these are ways that we can use energy to make predictions about the motion of an object. One last thing to note here, we've already predicted motion of objects with kinematics. The main difference between energy and kinematics is there's no time in any of these equations, right? Nothing energy will tell you is, it will not tell you how long something takes to happen, but it will tell you how fast, how high, how much it compresses a spring in this particular type of problem.